picking up where we left off. Limits were the key ingredient in the discovery of calculus and are essential in the development of differentiation, integration, and infinite series. So derivatives, antiderivatives, and series. We'll learn about derivatives and antiderivatives in this class, Calculus AB. And if you take BC, you'll learn about infinite series. That's Calculus 2. So limits as a definition has one condition. Its one condition is that the x value can only be approached, never arrived at. So we're getting closer and closer to an x value, but we never actually get to the x value. The limit is just as we're going towards it, the limit is equal to the intended y value of the function as x equals a is approached. It's not always equal to f of a, the actual y value. So here we have the limit of f of x as x approaches infinity. We should know this as in behavior. So we look at a graph or an equation of f of x and determine where the y values of a function go as the x values increase infinitely. And then we have the limit of f of x as x approaches negative infinity. Again, we look at the graph or the equation and determine where the y values of the function go as the x values decrease infinitely. So remember, the derivative is a synonym for slope and instantaneous rate of change and the slope of the tangent line at the point of tangency. F prime of x is notation for the derivative of f of x at x equals a. So if we connect the two, remember the instantaneous rate of change of f of x at x equals a. So the instantaneous rate of change is the derivative at one point, so f prime of a is equal to the limit of f of x minus f of a over x minus a as x approaches a. So the derivative as x at x equals a is equal to the limit of the slope as x approaches a. So we'll work with this definition of a derivative a lot. So the limit existence theorem. For a limit to exist, the limit from the left of the x value must equal the limit from the right of the x value, and they must both equal a real number. So infinity and negative infinity are not real numbers. They're not measurable. They're just theory. They can tell us where a graph or a function is going, but it's not a real number. So the limit from the left is denoted as the limit of f of x as x approaches a with a little minus sign after the a, not before it. The plus and minus after the number tell us whether we should approach the value from the left or the right. From the right, we have the limit of f of x as x approaches a from the right with a little plus sign after the a. A double-sided limit means we need to approach the x value from both directions. And there we just have the limit of f of x as x approaches a. So if the left or the right are not denoted, we approach the x value from both directions, the left and the right. So the limit existence theorem says a limit exists if and only if the limit of f of x as x approaches a from the left equals the limit of f of x as x approaches a from the right, and they both equal a real number. So a limit does not exist when it's infinite, meaning it's going off to positive or negative infinity. So an infinite limit would look like something like this, where we would have a vertical asymptote. Well, the limit from the left, if we approach, make this a, so the limit of f of x as x approaches a from the left is going up to positive infinity, but from the right, it's going down to negative infinity. So therefore, three little dots in the form of a triangle, that's shorthand for therefore, the limit does not exist. Right? It only exists if it's a real number. So again, therefore, the limit does not exist. So the limit as x approaches a does not exist, one, because the left and the right don't match, but two, even if they did match, they were both going to positive infinity or both going to negative infinity, it still would not exist because it's not approaching a real number. It's continuing in that direction. Oscillating means it's going up and down forever. So we see this in trig functions a lot. So if I'm getting closer to 0 and the function's going up and down more, then the limit as x approaches 0 from either direction is not going to exist because it's continuing to change. It's not leveling off at one number, it's oscillating, going up and down. So think of like a heartbeat or a trig function continuing to go up and down. The other time a limit does not exist is when the limit from the left does not equal the limit from the right. So this is called a jump. So if we have part of a parabola and then a straight line. Well, the limit from the left is going to approach this y value. Let's call it -1. And the limit from the right is going to approach the positive y value. Let's call it +1. So the limit from the left does not equal the limit from the right. We see these in piecewise functions, and this is called a jump. Okay, vertical and horizontal asymptotes based on the limit definition. So you need to know the limit definition of vertical and horizontal asymptotes. not just what they look like. So horizontal asymptotes exist when a function levels off at a constant y value as x approaches positive or negative infinity. So at most, we could have two horizontal asymptotes. So y equals b is a horizontal asymptote if the limit as x approaches infinity of f of x equals b, or the limit as x approaches negative infinity of f of x equals b. Again, where b is a constant. So horizontal asymptotes are the end behavior of a function. As x goes to positive infinity, the x's are growing. If they're all leveling off at a number, then we have a horizontal asymptote at that number. The limit as x approaches negative infinity, as the x's continue to get smaller and smaller. If the function levels off at a y value, at a number, then we have a horizontal asymptote at y equals that number. Okay, vertical asymptotes, we switch the infinities and the constants. Vertical asymptotes exist when the limit as x approaches a real number is equal to positive or negative infinity. So x equals a is a vertical asymptote if the limit as x approaches a from the left equals positive or negative infinity, or the limit as x approaches a from the right equals positive or negative infinity. We only need one of those to prove that a vertical asymptote exists. If you're going off to positive or negative infinity in one direction, as you're approaching a real number, then you must be running into a vertical asymptote. So notice how the constants in the infinities are switched for horizontal versus vertical asymptotes. Horizontal, x goes towards positive and negative infinity, and it equals a constant. Vertical asymptotes, we go towards a constant, towards a real number, and the limit equals positive or negative infinity. Okay, continuity is one of the big definitions of this unit. A function is continuous at a point if the double-sided limit is equal to the y value at that point. So the double-sided limit is denoted as the limit of f of x as x approaches a. So we need to approach a from both directions. If that equals the y value at f of a, then the function is continuous at x equals a. So the three types of discontinuity. Unbounded means infinite, right, where we have vertical asymptotes. Algebraically, it would look like a number over 0. If we get 0 in the denominator, but have a number in the numerator, this doesn't prove, but it implies a vertical asymptote. It's the definition of a vertical asymptote that would prove that there's a vertical asymptote there. Jump discontinuity shows up in piecewise functions when the limit from the left does not equal the limit from the right. Graphically, it looks like the functions do not meet at the same y value. So I drew a picture of a jump here. And removable discontinuity, also called point discontinuity, graphically it looks like a hole. So if we have a function but there's a hole in it, even if it's replaced somewhere else, that's still a discontinuity. A function is discontinuous if at any point when tracing the function from left to right on a graph, you have to pick up your pencil to fill it in. So here we'd have to pick up our pencil and fill in that hole at, let's say, x equals 1. Algebraically, it occurs when factors cancel out of a rational function. So, for example, if we had, it would be x minus 1 over x minus 1, and then we would still, maybe there's another extra x up here. Well, x minus 1's cancel out, leaving a hole in the graph at x equals 1. So wherever that factor equals 0. And x minus 1 equals 0 at x equals 1. Numerically, this happens when the limit, the double-sided limit, does not equal the y value. So here, the double-sided limit would equal, let's call this y value 2, and this one 4. So the limit will exist at a hole, but it's not continuous. So the limit as x approaches 1 from both directions equals 2. Remember, we're approaching 1. We never actually get to x equals 1 to fall into that hole. But f of 1, the y value at 1 is 4, is defined at y equals 4. So if the double-sided limit does not equal the y value, that indicates that we have a hole at x equals a. So a function must be continuous to apply the most important calculus theorems. Visually, the graph of the function will have no holes, breaks, jumps, or asymptotes. A continuous function is simply a smooth curve that can be drawn completely without lifting your pencil. So limits tell us where the function intends to go, and continuity guarantees the function made it there. So functions that are already continuous. Polynomial functions. So x, x squared, x to the third, x to the fourth, x to the fifth. Any combination of those, polynomial functions are continuous. Radical functions, square root of x, look like this, and are continuous functions. Exponential, whether it's growth or decay, are continuous functions. Logarithmic are more this shape, also continuous. Sine, let's see, sine starts at 0, goes up, then down. Cosine starts at 1, goes down, then back up. Also continuous functions. Okay, let's look at the properties of limits. So define the following in terms of L and M. So we're going to say the limit of f of x as x approaches a equals L, and the limit of f of x as x approaches a, g of x equals m. So if we're adding two functions together and trying to find the limit, well, we break the limit up at the operation. So the operation meaning add, subtract, multiply, or divide. So we're going to break it up at addition. So I'm going to rewrite it as two limits both as x approaches a of f of x plus g of x. So we break it up at addition. The limit as x approaches a of f of x is L, plus the limit as x approaches a of g of x is m. So we would find the limits separately, add them together. Subtraction is going to work the same way. We're going to break it up at subtraction. So the limit of f of x as x approaches a minus the limit of g of x as x approaches a, be L minus m. Division is going to behave just like you think it would. We're going to break it up at division, or rewrite it with a limit at the top divided by a limit at the bottom. So this would be L divided by m. So we find the limits separately, then do the operation. Multiplication, we're going to break it up at multiplication. And 5 is just a special case of 4 to it, where c is a constant. So if we have a constant multiplied by the function, we can pull the constant out front. So this would be equal to c times the limit. So c times L in this case. So find the limit, multiply by the constant. If we have a power, we're going to find the limit first and then raise it to that power. So this will be equal to the limit as x approaches a of f of x, and then the entire thing is raised to that power. So L to the p power. And the limit as x approaches a of a constant, remember, this is the function. So if I have f of x equals c, that's the same as y equals c, or y equals any number. That's just a horizontal line. And if we approach any number, it's going to go to that c value. This is going to equal c, the constant. So for example, if we have f of x equals 3, that's the horizontal line, y equals 3, and the limit is always going to approach 3. The y value is always going to be 3, so it's going to stay that constant. And the intermediate value theorem. So the limit existence theorem and the intermediate value theorem are the two theorems that you need to know and know well from Unit 1. So if a function is continuous, so it must be continuous on a closed interval. Closed interval just means that the values at f of a and f of b exist. Right? They're not holes, they're not asymptotes. It exists. And if w is any number between f of a and f of b, those are y values. Remember, f of a is a y value. It's actually the starting y value in this case. And the ending y value. So if w is any number in between the starting and ending y values, then there's at least one number c between a and b such that f of c equals w. So c is an x value in between a and b that will take us to that desired y value. So in words, if a function is continuous between the starting and ending x values, then every y value between the starting and ending y values are guaranteed to exist. So if a function is continuous in between its starting and ending x values, then every y value between the starting and ending y values are guaranteed to exist. So graphically it looks like this. So f of a, x equals a, and x equals b. We can see that the function is continuous between a and b, right? I can draw from a to b without ever lifting my pencil. And the values at f of a and f of b exist, right? There's a point at f of a and there's a point at f of b. So I know it's continuous and closed. Then what that guarantees is all y values in between the starting and ending y value are guaranteed to exist. Essentially, we can't get from f of a to f of b without going through all the y values. So w is a y value, and it has to be between f of a and f of b. Well, then it will be guaranteed to exist. Right? And it'll exist at some x value in between a and b. So the conditions for IVT, or intermediate value theorem, are that the function has to be closed, it has to be continuous, and the desired y value is in between the starting and ending y values. So we can't apply or prove anything using this theorem unless the conditions are met. So when the conditions are met, the intermediate value theorem guarantees some x value between the starting and ending x values will take you to all y values between the starting and ending y values. So read through that a few more times to get the language in your head, and then when you do the practice, hopefully it will make more sense. Now, the squeeze theorem is here, and it is part of Unit 1. We're not going to practice it, nor am I going to assess you on it, but I'm going to tell you what it is. It's a pretty not super interesting theorem. So it says if g of x is smaller than f of x and f of x is less than or equal to h of x. So we've got three functions, one on top, one on the bottom, one in the middle. Then the limit of the lower, if the limit of the lower equals the limit of the upper, and they equal a real number, then the limit of the middle function will also go to that same number. So squeeze meaning the limit from the bottom function and the limit from the top function equal the same number, and the middle function is in between, then it's also going to equal that same number. So if one function is in between two other functions and they all happen to meet at the same y value, then their limits, as they all approach the x value, will be equal. So it has to line up perfectly to be applied, and it's just not all that applicable. Here you can see an example where we have this oscillating function in between the top and the bottom functions. So the limit as x approaches 0 here for all three functions is going to equal 0. Right? They're all three going to 0. Top's going to 0, the bottom's going to 0, the middle's in between, so therefore it's also going to 0. So again, without limits, there would be no continuity. We have to be able to define continuity or know whether a function is continuous in order to apply the calculus portion. Without continuity, there would be no derivatives. Without derivatives, there would be no integrals, and without integrals, there would be no calculus. So at this point, you should be able to read, write, and evaluate limits using their properties, use the limit definition of continuity to verify points of continuity and discontinuity, and verify and justify the conclusions of the limit existence and the intermediate value theorems.